Hello everyone, welcome to Swift Nuggets, an interesting episode, I promise to you. After WWDC and Liquid Glass and everything new, Xcode 26 and so on, today we're going to explore everything that came into Swift 6.2. I know we did in the last couple of videos, we explored some of the proposals from the language, but today is the time we have a proper Xcode, we can try the new things, and we're going to explore every proposal, like the most important ones, and do some demo projects, play around with the new stuff, new APIs, and so on. So yeah, we have Xcode 26, and now we're looking at beta 2, which came out on 24th of June. It requires Mac OS Sequoia. You don't need to install the new one. And what's amazing is that we have Swift 6.2 right here. And that's amazing. We don't have to install additional tool chains, make them work with Xcode to just try the new proposals. We have now an opportunity to just open Xcode and play there. And we have new versions of the iOS 26 SDK and some others like macOS 26 and the other like tvOS, visionOS, and watchOS. If I'm going through the release notes, I see a bunch of fixes on the beta 2, and as well some new features. Some of the resolved issues, which are also tied with Swift 6.2, are like added support for backtick escaped row identifiers. It fixed an Xcode that was crashing on launch when it tried to restore the UI state, and so on. By the way, I've done a small Xcode 26, what's new in Xcode 26 video. I also recommend what's new in Swift from WWDC. Yeah, that video plays well, and I strongly recommend you go through it. Nice. And what else? We have app intents, some issues with the app intents that got fixed. We also have some improvements over the span properties. There are still some known issues, like span property does not support the small string representation beta 1. You have a workaround to reserve like an UTF-6, UTF-8 code units if you want to force strings to use another representation. In the Xcode release notes, you have like some Swift code snippet that you can use if you're blocked by that. All right, and yeah, I was looking if we had some cache resolving updates in Xcode 26 beta. All right, for me, the build cache, there's a property in Xcode that caches builds and helps you with the build times as you incrementally build in Xcode, but it was broken for me. Maybe with Xcode beta 2, I will try and see if that got been fixed or not. Okay, I see here bundle does not refer to the correct resource bundle when used from a mergeable library. As a workaround, use bundle 4 instead and pass the class meta type. Okay, cool. I will share the link to Xcode release notes, but I think you can find it on your own as well. Now going to our GitHub, if I'm going to Swift Nuggets GitHub repository, right, let me share here. So I prepared in Xcode 26 playgrounds, small playgrounds, exemplifying that Swift proposal that was introduced as part of the Swift 6.2 update. You have everything here. I will share everything in the YouTube's description. You have Nonescapable Types examples, raw identifiers, inline arrays, and much more. I created a small SwiftUI application. I find it useful and very easy to do that like that. Of course, you can create a macOS app or like a simple playground where you play with the Swift 6.2 additions. But for me, I find it much comfortable if I just do the SwiftUI app and place in the code a small example project that it's getting run when the application starts or when the application renders the first screen, for example. And you have links to the proposals if you want to study more about them. And what's cool is that if you're using some kind of AI tool, like Cursor, Cloud Code, and so on, I've prepared here some notes, some cursor rules that you can use, which you can inject them into your cursor or into a prompt and into an LLM client and give them as a prompt. They have concepts like given an URL of a Swift proposal, provide an explanation. Please include a clear and concise summary, and you have some prompts that you can directly use in Cloud Code, Cursor, whatever, ChatGPT, and that if you pass an URL of a Swift proposal from GitHub, for example, they will explain you better. They will give you some examples of the code and so on, so you can learn better about the new things that were added with that proposal. I will share that. I mean, it's part of the repository, but everything will be included in the YouTube's video description, and as well with, I mean, you find it in the podcast description as well for the repository. All right, cool. You switch the branch. So in the video, in the podcast video, I'm sharing my Xcode. Let's put the initial one. And I have here the skeleton where like I tend to go through each proposal and populate the example functions here where we can play together with the new things that were added with 6.2. And let's start first with, by the way, if you go to the repository, let me switch here the branch to feature episode 4, links to the proposal that are part of each episode. So as I ramble here about the proposal, I've included also the links into the GitHub's description, but you also have it as a timeline into YouTube, for example. And today the plan is to go through all proposals for Swift 6.2. Let's start with the first one, isolated synchronous deinit. We already spoke a couple of times about it, but it's important to understand that with this feature, you're now able, this feature allows the deinit method of actors and global actor isolated classes to safely access their isolated state during stuff like cleanup or deallocating, of course. And you have this isolated deinit in front of your deinitializer. Before this proposal, this deinitialization could not access the non-sendable isolated state. And it was like severely limiting the usefulness of that method. The isolated keyword before deinit right now indicates the initializer should run on the actor's executor. That's very good if you want to have like a cleaning, if you want to clean your observers, notifications, canceling background tasks, for example, logging, debugging, you can place there your, I don't know, print statements, whatever, your logger output and so on. Or if you want to clear some cache or some temporary data. You should avoid for long-running stuff like file handles, network connections, clean connections, or yeah, like communicating with servers, long database operations, transactions, and so on. Something that is like critical to your resource management or is like taking a lot of time. There's also a safety benefit for this proposal. We're now like safe from a data race point of view. Before this, deinit could run on any thread, and we could lead to potential data races when we would access the isolated state. But now, having the deinit isolated, it will run on the correct executor, guaranteed safe access to isolated state. This makes like Swift's actor system more complete and practical for the real world use cases and for a proper cleanup, which is essential. If we have, let's create here a bunch of classes. If we have a friend, let's imagine a final class friend that has a state, which is a immutable integer, and we create a second class person. Let's do them as private inside this extension. And this person, it references the friend class. Let friend creates an immutable friend. And name is UUID string. Let's call the init without passing the friend. And inside the initializer, I'm going to print here a statement called init for name. So we know when this initializer is being called and for each name. And let's create friend equals like friend. I created an empty initializer which allocates the friend instance. And let's create another initializer, init other person, and here let's put person. And let's call this one called init for name. And here we call friend equals other person dot friend. So we reference the friend of the other person, the variable that is passed to the initializer. And deinit, let's do a print called deinit for, and here let's put the name. So we know this function is going to be called, and let's modify the state of that friend plus equal 1. As you probably imagine or see if you're watching the video podcast, we get an error if we're trying to modify the state of the friend state. An error that is saying the main actor isolated property state cannot be mutated from a non-isolated context. So clearly we have an error if we're doing that. But if we mark this as isolated, we are sure this will be called in the isolated context. So we are safe from this point of view. Okay, so let's try this out. Let's create a person, which is an optional variable, and let's pass flat person. But let's unwrap it and then create a separate person, other person equals person. This will call the deinit. Call deinit right away. If I'm not doing anything with the other variable, then yeah, it will call the deinit. And here I'm going to say the first person equals nil. This will call again the initializer. And let's run to see what's happening. Okay, so we see that the deinit has been called is from an isolated deinit. That piece of code worked. So this allowed me to use the global isolated class to safely access their isolated state during cleanup. Next one, Nonescapable Types. It touches the escapability. You have that tilde non-escapable, we spoke a couple of times. I won't go into that much details. But is a Swift 6.2 feature that allows you to create types with strict compile time, lifetime restrictions. These types cannot escape their original scope, meaning that they must be used locally inside of that function scope, for example, and cannot be stored in long-lived variables or returned from the functions. If I'm going here, non-escapable example types, let's see if it's working. I will create here a private enum not escapable. And if I put tilde escapable, all right, I can create one which is non-escapable. Let's create two values, case second value. See what's happening. And let's try to return, see that if it's working, escape second value. Let's try to return self here. And let's say return second value. Well, the compiler is now providing me an error. A method cannot return a non-escapable result, so it cannot escape this context. This will give me an error if I do that. But I can format the values, create a computed variable formatted that returns a string, and I can do a switch self, returning like the value. If I can also create a show syntax like this without the return, and this will work. Let's try it out here. Let's create not escapable value and pass it as a value. It will compile just fine. Non-borrowing. Let's create a function to see if we can pass it to a function. Private static func non-borrowing function, and here we can pass the not escapable value. We can pass that to do something here. We can do something here with the variable, but without like escaping the scope of it. Yeah, non-borrowing. value and it will compile just fine. And I can also do print value dot formatted and it will work just fine. All right, so now we have this new way of adding non-escapability to enums structures and so on, and it's quite cool if you limit the scope and have clear benefits about them. Span, safe access to contiguous storage. There are like a bunch of Swift proposals that are touching the span family. This creates like a good way to look inside the memory. We had those unsafe buffer pointers that like give us an kind of a not so cool, not safe, an unsafe way to look inside of zone of memory, or even if we would alter and mutate that the memory of the variable or whatever. We were not sure about it, and it introduced like weird errors and so on, and it was unsafe. But with spans, with this new abstraction introduced in Swift 6.2, we now have a safe and a performant access to the zone of memory which is contiguous. They're essentially a view into the memory that allows us to work with the data without actually copying it. We have spans, we have the MutableSpan, I have talked the RawSpan, sorry, but we also have MutableSpan and MutableRawSpan and new span. So we have safety guarantees. We have the temporal safety, cannot escape. Those spans are not escapable, and so it prevents use after free bugs. Every access is bounce checked at runtime, ensures the memory is properly initialized before access. We don't have unwanted copies. It prevents accidental copying of large data structures, for example. And we have two types of span as part of this proposal. The span type, which allows sharing the contiguous internal representation of a type, which is a type span for specific element types. But we also have RawSpan, which is an untyped span for raw memory access. What bounce checks actually means. In Swift, it means like it has a runtime verification. Every access checks if the index is valid. Control failure, if we get an out of bounds access, it will trigger directly a crash, a runtime trap. And you don't have like an undefined behavior, unlike C++. You don't get random memory corruption. Raw spans are the untyped counterpart of spans. They work with raw bytes instead of specific element types. And MutableSpan and MutableRawSpans are the type safe, exclusive mutation access that offer like mutation access to that zone of memory, that contiguous zone of memory. They are like the writable, the span and RawSpan are the view kind of things for viewing that zone of memory. But if we want to change that zone of memory, we have MutableSpan and MutableRawSpan, which are safe, exclusive, and they have a way to mutate the zone of memory. This allows us to modify that data in place while maintaining Swift's memory safety guarantees. Under the hood, when you do like, you allocate a buffer of numbers coming out of some bytes, you create a non-copyable view into the array storage. The span locks the array from other modifications. And if you perform mutations, it will perform those mutations directly through the span, modifying the array's memory. And then it's best to consume the span, the mutable span. If you consume it, then it will release the lock, the exclusive lock that it was put. Okay, so this with non-escapability brings like a lot of new additions to Swift 6.2. This increases the interoperability with other programming languages such as C, C++, and working directly with some APIs on the memory zones rather than relying on with unsafe buffers. And yeah, that was kind of not a good thing. So let's try to see if the APIs are working into our demo project. And let's create an array of numbers. Let's say that numbers 10, 20, 30, 40, 50, 60, and 7. Let's have 7 numbers. On the old way of accessing the zone of memory, you had like, you'd place, let's take a variable result and say number with unsafe buffer pointer. And it will do buffer in numbers here. And I have a warning, constant result inferred, which may be unexpected, that's normal, insert unsafe. Now I have a new warning inside the compiler. Expression uses unsafe constructs, but is not marked with unsafe. So let's apply this. And inside here, we would do like buffer.map. Buffer is this closure parameter. And let's do a string.init and join. Let's transform them to strings and then joined as with a separator of comma. And this asks me to place unsafe as well. And let's see the span unsafe buffer pointer. Let's see how the result is actually a string. And the buffer you see here is an unsafe buffer pointer pointing to the elements of the array here. If I do float, here the buffer will be a wrapper over the float elements here. Let's go to content view. Let's delete this one and run the span example. All right, so we see here like the buffer took those numbers and like created a string out of them. And with the new way, instead of doing it with unsafe buffer pointer and have a pointer to the array's contiguous storage, which is unsafe, now we have a safe way to do that. We can say directly let span equal numbers dot span, and that's it. We have a property added to arrays called span, and this will give us the actual bytes. And we can like access a number, accessing first element, and we can do like span 0. This will work perfectly fine. You see accessing first element 10. It works just fine. Let's bring the simulator there. But we might also want to work directly with the bytes, and here we have the RawSpan coming into play. And to do that, we can say span.bytes, and it will offer me access to the raw bytes. And I can check the RawSpan byte count, for example, say number of bytes here of raw bytes. This should be like, I have 8 bytes and I have 7 numbers, so it'll be like 56 bytes right here. Yeah, so I have the number of bytes in the span here. The complexity is 0.01, of course. And let's try also the MutableSpan. Let's say I have some bytes, an integer, say 1, 2, 3, 4, 5. Let's create a data out of those bytes, and I can say data bytes. Yeah, this one is the type. And MutableSpan, we can say data.MutableSpan or MutableRawSpan, mutable bytes. I'll choose MutableSpan. Let's go for each, for I in 0, MutableSpan.count. Let's multiply or do something with those bytes. Yeah, +1, let's do a multiply of 2. So each value should be 2, 4, 6, 8, 10, and so on. And let's consume. So we end the mutation and we use consume. And here replace the name of the variable MutableSpan. Let's convert them back to data, to bytes, and do another print, and print them. Print mutable, let's say MutableSpan bytes, and here we can say bytes, right? And this should be the results mutated on the zone of memory, okay? You see, it's like we had the initial values 1, 2, 3, 4, 5. After I mutated, I took the MutableSpan from the data, from the bytes. I mutated them simple for loop, and finally it gave me the results mutated. Yeah, how cool is that? And those were the span types, new thing. Let's check the raw identifiers, also called escaped identifiers. Is essentially adding backticks, allowing Swift to use identifiers that normally wouldn't be valid. You have here a few examples, like the test names. You had like a way that you put the Swift testing framework, like the name of the test in like normal language, and then you put another name of the function. But with this redesign, we can directly place the name of the function in a way that is more readable. Like, don't do the same thing twice, removing the redundancy of that function. It's something like this. So let's see if we can create an example here. Let's try out if we can create an enum first. I will do a private enum color shade enum, and let's create a bunch of cases. Backtick 50, 100 with backticks, 200 with backticks. It's clearly working. I don't have any kind of errors, compilation errors. But if you try into a previous Xcode, it will have the errors on you. I can also create some static function, like, let's imagine like a test when user logs in with valid credentials, then success. Print running test, like this. All right. And let's see if it's working. Let's create a light gray color, and I'll do color shade, the name of the enum dot, and here I have the options with backticks, that 50, that's 100, and so on. If I do print, it should contain the backticks as well. And the funny stuff, let's see how can we call the function. Like, we use backtick when user logs. And you see here, I have the, the function being suggested there. Okay, so it's working. Integer generic parameters. This proposal introduces the integer generic parameters. This is the ability to parameterize this kind of structures, the types and functions with integer values at compile time. Instead of providing that repeating stuff, if you remember, runtime values, you specify those ints as part of the type itself. Like you have struct vector let count, you put that let count integer and then the element in this example, in this particular example. Now, why should we do that? Well, we have them available now at compile time. We know precisely how many values those structures have. So instead of runtime values, you specify integers as part of the type, making them available at compile time. All right, and there are like some examples more with the vector territory matrix, and you have them as part of the proposal. Let's find our own example. Okay, with this new thing, in this new proposal, we can have declarations such as let vec3 equals vector, and here we can place the name 3, and what kind of elements do I expect. 1, 0, 2, 0, 3, 0. Of course, I need to create this vector. Let's do a private struct. And here we can say vector, and I put let count, which is an integer, an int, and then the element. Okay, don't forget to close here. Argument pass that takes no argument. All right, and we can create here class structure, whatever, which makes use of this let count. And we can say elements with char generic. And let's create a subscript here, index int, and return the element. Precondition, let's do a precondition index less than count, and return the element not index, right? And we have here the count, which is like this 3, but we need to be careful because here I can pass more than 3 elements. And if I do elements, the subscript that index, it will crash, of course. But yeah, we can like create some safe ways inside the structure to prevent this problem. Let's do print allocated vector vec3 here, and let's see what's vec3 0 in index 0. Let's see here vector 3. Right, it's like a normal array. It will give me this 1 because I'm accessing the first element, and the first element is 1. But as you can see, we now can insert this kind of integer, the generic parameters, right? And this proposal goes hand in hand with inline arrays, which are fixed arrays. The problem that this proposal solves, I mean, we spoke a bunch of times about it, but I'll do a small reminder. The problem is like Swift's arrays are always heap allocated and like dynamically sized, causing this kind of a performance overhead where you need to have compared to fixed size collections. Well, inline arrays knows the size and stores the elements directly in line. It will be stack and it will be like a known compile time size. Okay, so with this fixed size, which is determined at compile time, and this will make your stack allocated by put it on the stack instead of the heap. So you don't have any kind of heap allocations. And it supports non-copyable types. This is perfect for fixed size collections, performance critical code, even embedded data structures and operations where you need to have a guarantee over the memory layout, and like you don't have any kind of overhead about the allocations. All right. Same as the integer generic parameters, we can define here. Let's do a point inline array, and you see here it has the count and element of fixed size array, which is what we created previously. And I can say 3 and like this, right? Or double as we did last time in the type name, and we can say 1, 2, 0, 3. The 4 here. But you see it's like expected 3 elements in inline array, but got 4. So it's at compile time. I cannot like trick this variable to put more stuff into array than I originally set here. And you can omit this 3 and the double, the elements, because they will automatically be inferred from the values right here. In the compiler knows there are like 1, 2, 3 values, and those are doubles because I have 0.0 here. See for yourself. Nice inline array here. It's like 3 and double. And let's do a print 0.0. Let's do 0.1 and see what it returns. And you see it accesses the second element. So these are quite fast arrays, inline arrays or fast arrays, I would call them. All right, and let's go to the next one. We spoke about spans and how they were like added to the standard library types. I expect more library types to be enhanced with spans because they are very useful if you have to work directly with the zones of memory and relying on the safety guarantees that Swift brings you. I always call this attosecond for some reason, but it's attosecond. There's like a very tiny piece of a second, And I spoke about it in the past, is like it simplifies the time measurement with high precision, enhancing this type, duration, a Swiss duration type, and it provides now a direct access to attoseconds values using a 128 integer. If an attosecond is like 10 to the minus 18 seconds, that's like 1 followed by 18 zeros. That's incredibly small. 0.0000001. And maybe you have a physics project that works with this kind of tiny elements, and it simplifies how you transform the elements. The limitation was like the bits were like 64, and that could not hold this enormous precision value. And now you have a direct access to the total duration, and you eliminate the complex component arithmetic. You don't have to do some kind of a math to get a view on how many attoseconds are in your calculations. There are like some constant conversions, which created some performance gaps. And you have a full int 128 precision maintained throughout the calculations. This is not a breaking API change. It doesn't break your code, and it's an additive one. It enhances the existing APIs. This makes duration, the type duration, much more friendly for scenarios requiring precise time measurements, performance profiling, scientific calculations, or high-frequency operations. Let's do some scientific explorations right now into our playground. Let's create first, let's see first before how it was like before this introduction to the duration type. Let's see here, private static function, average duration. Let's create a function average duration that takes in an array of durations and calculates the final duration. Let's create a count, a total that will count the attoseconds. I will declare it as 128, hold like that weird long number. Let's do here a constant static let attoseconds in second int 128. It will be 1 0 0 0 0 0 0 6, this kind of 6 18 3 6 9 12 15 18, right? 4 5 6, yeah. Whew, that's a lot. All right, so let's do for duration iterations. Let's do for in loop. And what we had to do before is to make those split into components. Like we had the duration dot components. This is the composite components of the durations of the duration. And then you'll do like total. Let's add attoseconds. It will be plus equal. Let's do a count. And then you'll have to transform those components into int 128 components.seconds multiplied by attoseconds in second plus that attosecond. So it holds the duration in seconds, plus it had a separate component for the attosecond. So it didn't provide a one and only view to that. And then you'll do like average total attos divided by the number of durations. We're calculating the average duration, having all of those duration elements. No simple average. And then with this, I would need a reminder, the quotient and reminder of these values divided by the given value. Attoseconds in seconds. Okay. And finally, once I do the calculation, I will have to return it as two components, the seconds component and the attoseconds component. You see here, there are like one is a 64 integer. And then I'll have to convert back seconds and here in 64 seconds. That's quite heavy. I mean, you need to have a count here. You need to take the components, make them into the same unit, the attosecond. Then you'll probably create this average and calculate it and transform them back into the seconds component, the attoseconds component. Whoa, heavy. So we had a lot of stuff to do, but now with the new API, let's create private static function average duration new and send the durations array. Send back the average of those durations. We can say total durations at reduce 0. And what should we add inside of this 0? We can say 0 plus attoseconds. Like we directly have these attoseconds here. And return the. So we do a sum of all attoseconds. This part is now like, instead of having that for loop and so on, you just do it one liner with the reduce function. And you have duration attoseconds directly. You don't have to use any more of those components. And you can say total divided by int 128 durations.count. So you need to transform the count of those durations into this integer 128. So you can have the real value here. Right, so there's like 2 lines of code instead of this big function. Let's see how accurate the results are. Let's create average old, do an average duration with old API. Let's say seconds. Sorry, this would be an array of seconds. Let's say 1, 2, and 3. This will give me probably the 2, right? I need 2 seconds because this is the average, and also average new, and do a print. Average old way, average old. Components, let's do them in seconds, and let's show them in seconds, and the new way, average new components.seconds. And let's see with the new total with the new API, because we didn't have this before. You can say average new dot attoseconds, right? Let's run and see the result. Okay, so I see the results are matching. I haven't produced any kind of weird errors. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Whoa, that's a long number. But of course, those are not like, you can have 1.1, you can have like this kind of seconds, 3.2. And this like takes the seconds part. It's an integer here. It will round to the 2 seconds, and you have this kind of attosecond, right? Have this part, right? Cool. So much better. Opt-in strict memory safety checking. This is an important proposal 458. Right, and with this opt-in strict memory safety checking, this proposal introduces the strict memory safety checking to help us identify and minimize unsafe code patterns, essentially. The motivation stems from a critical security concern. More than 70%, you see here in the motivation part, approximately 70% of security vulnerabilities in system programming are related to this part with the memory safety issues. While Swift is very good at memory safe and is by design intended to be a memory safe language, it still provides like some escape holes, some loopholes, like unsafe pointer for system level programming. We saw like spans now are like offering a much safer view with that. And developers may unknowingly introduce memory safety risks without realizing. Well, with this solution, we have compile time warnings for unsafe constructs, allowing teams to audit and minimize their use of potentially dangerous APIs. What does it mean? Like we have three main components introduced here in the proposal. We have a compiler flag, a strict memory safety check. We have new attributes. We have at unsafe, which marks the declaration that use unsafe constructs. At safe, right here, that indicates a declaration with unsafe elements, which we are like saying, all right, those are safe. We verified we are good about that. And some annotations like unsafe expressions, explicitly making unsafe constructs usage like try or wait. This is similar to try and wait. And finally, you have a conditional compilation. If the feature, if let's search here, if has right here, if has feature strict memory safety, you have this macro code will compile inside of it. Let's play around with the new attributes. Let's create an array here, array of integers 10, 20, 30, 40. And you saw that array with unsafe buffer pointer. Here's the pointer. And I can do something with the result. Let's do a sum int buffer. And we'll pass the buffer and the count of the array, the count of this array. And we create here a function buffer, sum int buffer, and take the address, the buffer, which is an unsafe pointer. I will use integer because I know the elements are integers here. I don't want to create any kind of generics right now. And the count is also an integer. All right, and this should return the int because we are summing up all the numbers here. It will be 10, 20, 30, 40, like 100. And we can say got let address to unwrap the address, the pointer. Else, what should we do? Return 0 probably, or -1. Let's do 0. Create a sum, 0, an integer, and then let's do for e in 0, e less than count. And here we do sum plus equal the address. Let's call it buffer. Buffer okay. Sorry, buffer here. Sum plus equal buffer. And finally return the sum. Okay. Cannot convert time to save the buffer pointer here. I did Control M and now the parameters are split on the new lines much better. And you can see I already have some warnings. We have like expression uses unsafe constructs, but it's not marked with unsafe. All right. Insert unsafe. Oh, okay. I need to do stuff here. And what else? Expression using unsafe constructs. Hey, watch out. Your code is unsafe. Please mark it as you have. And if I put unsafe, then I can like go make those errors suffer. Save let buffer equals buffer, and here I put unsafe. Sum equals unsafe everywhere. Right. And finally, I have here the expression uses some unsafe stuff, and is not marked with safe. And here we can say to the function that is unsafe, at unsafe, and put unsafe here. We also can mark the function with unsafe. All right, and here let's print the result. Some is result. Let's see if like it created 100 there as a output. All right, so it did that for us. But yeah, the methods, the APIs here are unsafe. And we also can mark something safe if you want. If we get that warning, such as like we know that the code inside of it is safe. Let's create here a private structure safe array. And let's use a buffer, which is a safe buffer pointer, integer, whatever, var variable, mutable variable here. Let's allocate it. And the allocation, I will not put the unsafe buffer pointer as a reference, but I will take the array of the integers there. And let's do it first, like put the nil zone here, and then array with unsafe buffer pointer. And here I would copy the bytes inside of my buffer. That buffer equals buffer. Right, so I've done that. And now let's expose the subscript. Given an index, I want to return the element of that index. And we can say unsafe buffer index. And it's not that safe, but for some reason we know that this won't produce any kind of surprises, and we can say safe. We explicitly mark this structure as safe, despite it's using unsafe internals. And you saw the warnings I got away. All right. And if we do print, let's do safe array, and let's access second element, safe array. And the second element, 0, 1, 2, the third element is 30. And you see it here in the console. Run non-isolated async functions on the callers actor by default. This proposal fixes a major confusion and safety issue in Swift's actor isolation model. In the previous 6.1 and so before, non-isolated async and sync functions behave differently regarding actor isolation, creating unexpected data races and making it difficult to write safe concurrent code. The problem is like non-isolated async functions always switched off the current actor, even when it's unnecessarily and potentially dangerous. The solution with this proposal is that the non-isolated async functions run on the callers actor by default. That's important to remember, with explicit opt-out functions that need to switch actors. You have two main concepts as part of this function. You have the default behavior, which changes. Non-isolated async functions now preserve the callers actor context by default. And you have new attributes. You have add concurrent. Concurrent. See here. Which makes functions explicitly switch off the current actor. But you also have non-isolated, non-sending right here. Functions that run on callers actor. This is the new default. Let's create a class, private final class, my class. Let's have a mutable integer value and have two functions here, perform async. Before this async function was non-isolated. So before non-isolated async. So it always switched off the actor. Now runs on colors actor. Value plus equal 1. Okay. And have here a perform sync function. We have the same behavior as before. This is non-isolated sync, so stays on colors actor plus equal 1. Let's mutate and increment the value, for example. And let's do a third function, fetch data, which is a sync and returns a data object. And we can say return data. And we can mark this as concurrent. So with this add concurrent, we explicitly switch off the current actor. Switch off current actor. So this will run in a background actor thread. It's safe to do blocking IO here. Okay. What about actors? Let's do an actor, private actor, my actor. Let's reference that class. My class equals my class, sorry. And let's see what happens if I do use object create a function here. Let's do it sync function. And before, this would lead to a data race warning because it's in the previous behavior it's switched off the main actor. Okay, but now it's safe. If I do my class perform sync, or my class perform sync. I mean, yeah, I need to call await even it's like a sync function because I'm in an actor. It stays on actor, this part. And if I do process data, let's do a sync and do that my class fetch data await. This will switch to the background, code. And here, after it's done, continues back on actor, on this actor. Okay, let's call those task. I'm doing in the main function task actor equals my actor, an actor use object, an actor process data wait. I mean, we use the wait, and this needs to go here inside the task because here we'll resume execution. Okay, yeah, I mean, nothing to print on the console, but it's important to know those kind of like changes into the behavior and use this set concurrent to run like switch off the current actor. Task priority escalation APIs. As the name infers, like it has to do something with task priorities. And it introduces a manual task priority escalation APIs to handle complex concurrency scenarios where the Swift's automatic priority inheritance, the one that provides by Swift, is not enough. It targets unstructured concurrency cases where tasks need explicitly priority management. In structured concurrency, Swift automatically inherits task priorities, but in unstructured concurrency, like async sequences, libraries, or IPC, I don't know, the task may need manual priority escalation that the current system cannot handle automatically. And with this proposal, we have a way to manually trigger those escalations and handle the priorities better. We have two new API changes, two new APIs, not changes. We have with task priority escalation handler, and we can say task.escalate priority. I'm not sure if it's part here. And the task priority has different levels. You have the background, you have utility, the default, user initiated, for example, high, low, and so on. And child tasks, if you create a task out of another task, it will inherit the parent's priority. With priority escalations, when a higher priority task waits on a lower priority task, the lower priority task gets boosted. All right, so let's create first a background task. And how we create a task, we can say task, and here we can say priority, and we can put background, and let's keep the operation. Let's do like current priority of this task, task.current priority. This should print background. Now if I'm doing I'm calling the new API with task priority escalation handler, I see a bunch of new stuff. Here, I think this is the old and this is the new priority. Priority, new priority. Async, I need to wait for it. And inside here, let's imagine we need to call a data function, load data, an async function. And let's do like loading data. Here we'll need some heavy operations with data. I'm creating a convenience method here, wait for seconds, let's wait seconds, and then completed loading data. All right. Wait seconds is like task sleep, for seconds I pass. It's an utility function here. And we call that function, load data, in the priority escalation handler. Let's see now, escalated priority, task current priority. And let's do like a wait seconds 3. Okay. And this should end here. Let's end. According to the sequence, like if I'm letting it here, it will be called first, so it's incorrect because the end is like after this timeout period, essentially. Then see like old priority here, and see here print new priority. Okay, so we have a bunch of prints here. Cool. So I created a background task, and that background task, as part of it, I'm calling with task priority escalation handler. I'm inside of that handler, I'm calling load data, and I provide a 3 seconds timeout here. Finally, let's run everything after a small delay, and I'll do the classic dispatch queue main async after. Let's do now plus 1 second. And what should we put here? Let's escalate the priority of the task. Say background task, which was like set to background priority. Let's put it to low and see what happens. You see the console. All right, so it current priority started with background, then it called the loading data function here, and then it started to wait for 2 seconds. Now this handler started, this handler with the dispatch main async after it's being called, and it sets the priority to low. The value, the change is being captured in on priority escalated, and I see here like the old priority was background and the new priority is now put it to low, which like changes if I have multiple threads. It will probably take more time for this part to be called. Okay, and finally, after the loading data completed, we have called here the current priority and is low once again. The next proposal, import Objective-C completion handler parameters as at sendable, is an interesting one because like when you had to work with Objective-C APIs, and they are still part of some Cocoa frameworks like location and so on, we had the completion handlers weren't put it as at sendable. Whenever we imported that, it created some kind of a problem. When you call these APIs from actor isolated contexts like main actor, Swift cannot guarantee the completion handler won't cause data races, leading to runtime assertions and crashes. That's like the purpose of Swift concurrency, make it safer, and we didn't have this before this proposal. The key changes are like automatic sendable import, Objective-C completion handlers parameters are now automatically imported as @sendable by default. This only applies when the Objective-C method is non-isolated. In case like you need a non-isolated context requirement, and you also have a way to opt out. You can put @non-sendable in Clang headers to override this behavior. But you also get like Swift6 warnings, provide compiler warnings for potential concurrency issues. If you remember, the sendable attribute indicates that the closure or whatever you pass can be safely passed across actor boundaries. What does it mean? It means that the closure doesn't capture the mutable state, and any captured values are either value types or thread safe reference types. The closure can be called from any actor without causing data races. And now we move to actor isolation, the concept. Each actor has its own execution context. When we cross boundaries from an actor to like some other part, created the problem. Like we need to guarantee the shared data won't cause data races. And with @sendable, we have this guarantee like, all right, it's fine to cross boundaries and we are safe. We don't introduce some kind of a data races. And we mark that with @sendable. Okay, another proposal about non-escapable types, we spoke about that, is like this proposal adds the non-escapable types to the standard library primitives. This proposal extends the Swift standard library to support non-escapable types in constructs like optional, the enum optional, and result. The core motivation to work seamlessly with non-escapable values while preserving their lifetime constraints. Non-escapable types, we spoke earlier, are values that cannot outline their original scope, so they are bound to a specific lifetimes and cannot escape that type. I won't go again into the details there. Next proposal, control default actor isolation inference. It's an important one and introduce a way to make Swift modules single-threaded by default. The essence of 6.2, and this addresses a fundamental tension with the concurrency model introduced with Swift6. The core problem is that the strict concurrency checking can produce false positive data race warnings for programs that are like single-threaded. I don't need to create this kind of noise and unnecessary friction for developers who don't need or don't want to introduce concurrency into their application. Swift becomes more approachable, especially for beginners, and we have a way to opt into a simpler mental model where all code runs on the main thread and that's it. All right, and we have new things like a new compiler flag, default isolation. Default isolation main actor, which makes annotated declarations default to main actor at main actor isolation. We have a SwiftPM integration where we put Swift settings default. Let's search for it here, default isolation, and there you put like main actor. This kind of settings. We have an opt-out way to use non-isolated keyword to explicitly request concurrent behavior. We saw in our demos. And this proposal like recommends that you use a progressive concurrency, gradual adoption of the concurrency features when you actually need them. And let's create here a function, say hello. Private static func, say hello, and say print hello. And if we want to explicitly mark like to not run on the main actor as we have here, we can say non-isolated to mark this function as non-isolated. All right. And let's create also a class. Let's call it UI controller. Let's put a mutable variable var is loading equal false. Let's create a function start loading We usually have this like when we create a new view or new view controller, the state where when we go and fetch data, we actually provide a loading state for it. And I say this loading equals true. Nothing fancy here. And stop loading. And here I will create a task. And then here main actor. Undo is loading equals false. Here, let's check the state. It's loading. I do a print. It's loading. And actually here, the function should complete if I'm going to call the controller. Let's do it here. Okay, if I do here non-isolated, it won't work. But here I can say non-isolated, stop loading, and I'm doing it as part of the task run on the main actor. Let's call this let controller equal UI controller, start and stop loading, and see what happens here. Controller is loading. Okay, so we saw in the previous demos and also here, all this is loading. So here, if I'm doing controller is loading, it will actually print true. You see here, and then it will do the false one. Okay. MutableSpan and MutableRawSpan we saw at first, at the beginning what they are. And let's go into the async stream continuation. It's quite nice. This proposal adds the hashable conformance, as you might guess from the title, to async stream continuations and async throwing stream continuations, addressing a common pain point when managing multiple async streams. In the current world, developers would have to track and manage multiple streams continuations, but can't use them directly in collections, like put them into a set or an array or dictionaries keys, because they lack that hashable conformance. So we now can put them with this new proposal into a set, for example. You can track those active stream continuations easily. You have like, you don't need to do like specific continuations with stream terminations and do like comparison operation and so on. And yeah, those are the cacheable values are computed based on the identity of the continuation, not the content. How can we check that? Let's create first, like, let's imagine a notification center we introduce, and that notification center will send some messages where we capture it into a monitor class. And for each message, we're going to store it as a set of continuations and subscribe to those notifications. Okay, so I'm doing a private final class custom notification center. I'm creating here a private array of continuations, like not private array, but private set of async stream, type string, because the message will be streams, continuation, and I'll make them empty at first. I will expose a public API called subscribe that sends back an async stream message. And here I'm going to create one with the closure based async stream continuation in continuations dot insert and put this new continuation that I created and provide the handler for the on termination part. And I'll do continuation dot on termination. What should we do here? Serve dot continuations dot remove the continuation. And because I need to put this into its own thread. Let's open a task here, which is going to be run on the main actor, and do like and put that. And yeah, on termination, I need to provide the closure. It's not like calling a closure itself. So a callback that's invoked when canceling the continuation, essentially. All right, so I have this subscribe, and let's create also a broadcast function. Message, yeah, and here we can say for continuation in continuations, loop through all continuations and call yield and the message. yield will resume the task, awaiting the next iteration point by having it return normally from its suspension time. Okay, that makes sense. So we created a custom notification center exposing two methods: subscribe, which uses a synced stream and adds to a set the continuations that I'm creating here. I provide a termination method run on the main actor that removes from the continuations the continuation, and the broadcast function that like broadcasts a string message iterating to the continuation that I have in the set. But we also need something like a monitor for my notifications. And I will create a separate class, notification manager monitor, maybe a better name. And this is kind of like a handler for those notifications. And I'm going to write notification monitor. I'm going to create a center here, the notification center, an array of tasks. Let's put them in never. Okay. Okay, right. And do the initializer. Let's create an empty list of tasks. Do not expose them as part of the initializer. I don't want that. And it's time to create subscribers, this function. And let's do some random 3 or 5, yeah. 3 subscribers, each of them having a task. Here I create a stream, notification center.subscribe. This will return me the sync stream from here. So I have the stream right there. And now whenever I receive a message, so for await message in stream, subscriber, and let's put the index, the I index number, I received the message, and here is the message. Message. I have a warning here, it's unsafe to use this API, so let's put unsafe. Await unsafe message, right? Because the message is unsafe, the one that is produced from that function. Okay. I created here the task. Now I call task.append and put the task. And that's fine. Let's also expose it. It would be nice to do a cleanup for it. Ask for each tasks. Let's cancel it. And let's remove everything from the array. Cleanup. All right, cool. So we have those 2 things created. Let's call them right here to see if they work. Let notification center. Let's create a custom notification center. Let's create a monitor. Notification center, all right. And here I would like to start, need to wait. Let's broadcast. Let's put an important message here. Let's put this emoji with the alien, Space Invader. Let's wait for 1 second or 2 seconds maybe. Oh wait, yeah. Let's do a cleanup. But we still need to create those dummy subscribers. And this is the key part. We subscribe there, and after, yeah, let's put here after 2 seconds we broadcast. And yeah, let's finally clean up. Okay, cool. All right, so you see here subscriber 321 received the message, and like that's the unordered. If I run it again, it will give me a different order of those subscribers, and I'm like preserving the order because I'm using a set there. But now, yeah, it's much better to, and much nicer for us to use a set and hold the references for the continuations, and like the code is cleaner. Thank you, Swift 6.2. Task naming. Oh, that goes hand in hand. What about task naming? The easy one to showcase. Introduces the ability to assign human readable names, like put strings or labels to the Swift tasks for debugging and observability purposes. Currently, without those names for the tasks, it was very hard to debug the concurrent code. It's difficult to identify which task was performing, which operation, like print statements. It was a mess. Making like bug hunting and performance kind of very challenging. And now with those kind of like those labels, the name to tasks is much better. You can use like profilers, debugging, and better logging tools, making concurrent code easier to debug. And how you set a name to an existing task, you just go here and place name, and let's say for notification, custom notification monitor task. And if I'm checking here, I can say here print task.name. No. So let's print the name of the task. Let's see, here is being printed. And what else? Global actor isolated conformances to conform to protocols while maintaining strict concurrency safety. Currently, global actor isolated types face significant challenges when conforming to protocols because their members can only be accessed from within their actor's isolation domain. Okay. Again, it cleans up and moves to that paradigm of everything is single threaded. Now we have at actor name annotation to protocol conformances. And I think in the proposal, we have some examples with the equatable protocol, where like if I have at main actor, which is by the way inferred, we don't need necessarily to put at main actor, but we can place the at directive, the actor annotation to the protocol conformance. Right, so let's see it. Let's create here a protocol, email sending, an email string get, and I also make it mutable with a setter. Let's create a final class user view model, which inherits the email sending, and the email is test@email.com. Okay. And if I would do like an extension, user view model equatable, and do the static func like this, before. So before this produced an error. I'm saying something like main actor isolated property email cannot be used to satisfy non-isolated requirement from protocol email sending. Right now we're having by default at main actor here, so we don't need to put it, and also here is like main actor, but if you add a different actor, then you use this directive here. And that's it with the proposal for Swift 6.2. Oh, sorry, there's one more. The migration tooling part is this proposal should help us adopt the upcoming features in an easy way. There are some flags that have been added. You have a migrate suffix feature flag for upcoming features, so you can enable them with enable upcoming feature name migrate. And there's a new Swift package called migrate. All right, and this command will be like a package-wide migration, and there are like some other things like fix compiler provides automatic code transformation with warnings. We can migrate warnings organized by feature for clarity and so on. Cool, and that was about the Swift 6.2. There are a bunch of new proposals that are kind of new. Let's go through them. InlineArray type sugar introduces syntactic sugar for declaring InlineArray types, making fixed size array declarations more readable. Currently, you had like InlineArray and you have the type of the array, like 5, and then the integer as we saw previously. And now the idea is to have this 5 of int, or adds the x of int as a more natural alternative that reads like English and aligns with how developers conceptually think about these fixed size arrays. This would probably make Swift more approachable and consistent with other languages. Right. Method and initializer keypath, part of 0479 proposal. And this gives more power to keypaths, extends their functionality to include references to methods, and initializer enabling more dynamic and more functional programming patterns. Currently, you have keypaths working only with properties, and that limits their usefulness in functional programming, where you want probably to pass not just those variables, but some other stuff as well. The motivation is to unify how we reference different kinds of type members, properties, methods, and initializer, and provide a consistent API that enables more flexibility and more dynamic code patterns. Yeah, that's nice. Default actor isolation type alias. It's currently in active review, been for some time. And this introduces this new type alias called default isolation. And if you put this into a file, you'll have control over the default isolation setting. Here I'm seeing default isolation equals main actor, but you could put non-isolated, and this will change how the file, the code from the file behaves. Right now it's like all or nothing nature of module level default isolations. Sometimes you don't want that necessarily. You might want some parts to be like on a specific base, and you have like more control over this isolation using this new type alias. Yielding accessors introduces two new types, yielding borrow and yielding mutate. And if you check the getter, get and set, those are like alternative to the traditional get and set accessor, just for like performance and non-copyable types. Right here. Right, traditional accessors cannot work with non-copyable types since they require creating copies. This get and set, no, it's a limit that we currently have. And with yield, NuGet yield and NuGet borrow, with yield mutate and borrow, you can solve this problem. You lend direct access to their values without like creating a copy. Next one, 485. Oh yeah, OutputSpan. Span, RawSpan, MutableSpan, MutableRawSpan, and now we have OutputSpan. And OutputRawSpan is like continuing the span family, adding a safe abstraction for memory initialization. The core motivation is to provide a safer alternative to unsafe memory operations when containers need to delegate the initialization of their storage to user code. Currently, operations like arrays initializing or strings require unsafe functions that are error prone and can lead to memory safety issues. OutputSpan intends to solve that problem by providing a safe bounce check way to initialize the memory while it maintains the safety guarantees. Yeah, similar with the other functions, the other span family functions and types. Transactional observation values. This has been accepted. This proposal has been accepted and is tied with SwiftUI and describes a new way, safe, ergonomic, and composable way to observe changes into models using an async sequence. And this starts the transaction at the first will set and then emitting a value upon the transaction end at the first point of consistency. All right. To be precise, we have a new closure observations type that acts as a sequence of closure return values, emitting new values when something within that closure changes. Take, for example, this final class person that has two variables, first name and last name, and the computed variable name which computes the first name as a space between and the last name and returns the value. Well, we can create now an observer for that computed variable, like observer let names equals observation person.name. And it will create an async sequence that yields a value every time that compose property is updated. If this is more complex, like I'm having imagine like an optional variable pet, which is also observable, like I'm having a class pet and this is observable, then we can have something like this. If let pet person.pet, we can have an observer that basically tracks two types of things: the variable's name from the pet itself and the name of the person. It will track both the assignment of a new pet and then consequently the pet's name. Whoa, how cool is that? And yeah, we have more examples here of this new behavior. And final two proposals that I wanted to catch with you today. First one is about starting tasks synchronously from caller context. This introduces a new task that immediate, as you can see here, which creates that task and executes it synchronously on the current execution context until, very important, the first actual suspension point. You have right now a small initial scheduling delay for tasks, and now we have a precise call saying, oh, this one should be immediate synchronous right now. Gets queued and may not start immediately in the current world. And for tasks that might run quickly or need to execute certain operation in a sync way before suspending, this delay can be a bit problematic. Take, for example, the UI where like you have some code that needs to be run synchronously there. Cool. So you now go task.immediate and you start just right after that. Finally, warning control settings for Swift Package Manager 480 produces like warning control for compiler warnings behavior across C, C++, targets. You have a unified with this proposal, a type safe alternative to use those unsafe flags, if you remember, for warning configurations. And you have more control over those warnings. Before that, SPM users, you had to limit. You had not so many options for managing warnings. They could either accept default settings or resort to unsafe flags. But now we have a clean declarative API for warning management, as you can see here in the proposal. All right, people, we went through a lot of proposals today. We went through everything with Swift 6.2. Oh, that was very cool. I have prepared for you that demo playground is part of the repository. You can check. I will merge into the main branch, the examples. Go check them out, play with them. Very important. I will share with you that prompt. It's not part now of the repository, but of course. So I'm going to share that prompt that you can use directly and pass the link, the URL to the Swift proposal, and then you can explore more, learn more about that on your own. Thank you so much. Happy coding, happy release Xcode time. See you next time. Bye. Hip hop, like greatest story. Hip hop, like greatest story ever told and robbed. Hip hop, like